Okay, so here we are once again. This is our last example in this chapter. It's a very beautiful problem, so we're going to depict this a little bit and look at it. So you have a 200 grams, 40 centimeter diameter turntable, rotates frictionless and frictionless bearings at 60 RPM. So we have a mass here for the disc, we have a diameter, and we have an omega. And then you have a little block of 20 grams, so we'll call this M index B from block, sits at the center, and a compressed spring shoots the block out. It's kind of like you even can shoot it with your own finger, right? So shoot it out on outward along a frictionless groove in a surface. So, you know, this is a hard one to do in 3D, but I'm going to do a picture from the top. So here you go. Here's a first picture, an initial moment. And I have a little block sitting in the center. I'm going to do the diameter so I can center the block a little bit better. So here is my block sitting in the center. And now let's depict the second part. I'm going to do the same disc. I'm assuming that this block now is going to go on a groove towards the edge. Hey, I should have probably put a better way to look at it. Here you go. Even that. Let's see if I do. Oh, nope. Let's try this again. Okay. Here's the groove. I didn't want to lose the groove at all. Okay, let's try this again. Alrighty, here's the groove. Alright, so I'm gonna put my little block right in the center. So in the first phase, it's in the center. Now that it kicks out all the way to the edge, it's going to be positioned somewhere here. And everything is frictionless, so let's call this position 1. Let's call this position 2 of observation. And then this is moving with an omega 1. Right? And then this is going to be moving now. That will change with omega 2. We have this mass M. This right here is mass of the block. Mass M of the disk, mass of the block. And I think I kind of depict everything I wanted to show here. Alright, so a compressed spring shoots the block out radially. Let's assume that happened. Then we look at from the top and we see picture number 2. What is the turntable rotation angular velocity? So essentially they ask you, hey, what is now omega 2? When the block reaches the outer edge. So we are hunting for omega 2 radians per second, or by the way, it could be in RPMs, since the original one is also in RPM. So what's happening in this problem? So try to think about, maybe pause the video and think about what happens here, right? Think about conservation. In terms of conservation, who conserves? What happens? Okay. So assuming that you actually stopped the video and you thought about it, I was expecting that you probably thought about the fact that the angular momentum is conserved, right? Okay, is conserved. And so this is the model. You have a rigid disc, right? Then you have the bearings underneath. The bearings and the spring have absolutely no capacity in here other than just putting the problem together, right? So then all of a sudden a particle out of this moves from center to the edge. That's it. Once it does that, the omega changes. But the whole angular momentum is conserved. Why? You have a momentum of inertia right here. That's part of it, right? So L is nothing else but your omega I. So this is the only part that you can focus on. How do you find this omega? Yeah. So for that moment, for that reason, we have to find, first, we have to find out, hey, what is my moment of inertia of the turntable in phase 1? So in phase 1, it's nothing else but the disk right? Plus whatever that little piece brings in the middle, which is the mass of the block times the radius from the center of mass, but that is 0, right? It sits right in the center. It will bring no participation. So this is 0 squared, right? Because our I, just remember that in general is mr squared. Or you can do the integration, right? So right now we are here with a disk. We know that the disk is the one that brings in together the initial moment of inertia. So let's plug in our numbers and find out what do we get here for that. So what do we get? The disk is 1/2 mr squared plus 0, okay, just to be kosher here about everything. So in our case right here, we get, what is that, 0.2. So 1/2 times 0.200. Those are kilograms. And then we talk about the radius. Diameter is 40, radius is 0.2. So 0.2, those are meters all squared. So essentially we get 0.0040 kilograms meter squared. All right, so now as the block moves out, this final moment of inertia will change. So I'm going to call that one I2, just to depict the same pictures here. Right, so it is equal to the I of the disk again, plus the mass of the block times radius squared. Because now, all of a sudden, the position of the block is 1 radius away. So I2, since we already calculate I of the disk, which was equal to I1, that is 0.0040 plus mass of the block, okay, so that is 20 grams, so that's 0.020 in this case, kilograms. I should have put here kilograms meter squared. Right, we are adding apples and apples here. Times the radius square, so that would be 20 again, 20 centimeters, so that's 0.2. So those are meters squared. All right, so by the time you're done here calculating, let's see what we get. 0.0040 plus 0. So that's square, so that would be 28. So 0.0008, I believe it's only 3 zeros. Okay, so these are all in kilograms meter squared. Final answer here for that becomes 0.0048. All right, so now that we do have our moment of inertia for each case, and we are to combine, we have omega 1, right? The omega 1 here, I'm going to put a 1 right next to it. This is the one that was given at 60 RPM. So if we leave it alone in RPM, and when we do the angular momentum conservation, then our final answer will be in RPM. So now we have conservation of the angular momentum. So we have omega 1, I1, must be equal to omega 2, I2. Okay, so from here you get omega 2, because that's what we are hunting for, is equal to I1 omega 1 over I2. All right, let's plug in what we have. I1 was 0.0. You know, you can put them in scientific notation as well. In the end, I don't think it matters, as long as you put the units correctly, okay? So that will be in RPM in the end. Since the kilograms meters squared will simplify out, divide by 0.0048. And using your calculators, you get 50 RPM. All right, so let's kind of think if it's correct or not. What do you think? You know, common sense, what is that telling you? If a change in angular velocity, it goes, in this case, from a 60 to a 50, right? With an increase of value of the moment of inertia. So that's reasonable, right? That's the reason the conservation happens here. So that's it for this video. Thank you, and have a good day.